Simplify inhibition. Before we talk about inhibition, you need to know how to read these two charts. If you don't, watch my lesson on enzymes and enzyme regulation now. In competitive inhibition, the inhibitor competes with the substrate to bind for the enzyme. This will increase Km, but Vmax stays the same because the number of functional enzymes in the solution remains the same. In other words, competitive inhibition can be overcome by increasing substrate concentration. Looking at our Lineweaver-Burke plot, Vmax stays the same, so the y-intercept doesn't change. The x-intercept gets closer to 0 because Km increases here. One easy way to remember this relationship is like this. If we take half and increase the 2 to 1,000, we can see the fraction gets much smaller. 1 over 1,000 is basically 0. So again, as you increase a denominator, that term becomes smaller. And this doesn't change whether a fraction is positive or negative. In uncompetitive inhibition, the inhibitor binds to the enzyme substrate complex, knocking the enzyme out of the equation. This lowers Vmax because you have less enzymes available to work. This also lowers Km because of Le Chatelier's principle pulling the equation in this direction, which increases the affinity of the enzyme for the substrate. Looking at our Lineweaver-Burke, the y-intercept gets farther away from 0 because Vmax gets lower, and the x-intercept is also farther away from 0 because the denominator term got smaller. In non-competitive inhibition, the inhibitor can bind either the enzyme or the enzyme substrate complex, and it does so 50-50. Because both sides of the equation are affected equally, Km is the same. Because enzymes are taken out of the equation, Vmax decreases. Looking at our Lineweaver-Burke plot here, Km doesn't change, so the x-intercept is the same. Vmax decreases, so the denominator gets smaller, so the y-intercept is farther away from 0. And that's how we can